I think
Alrighty.
Two sections and you talk about.
Yeah. Yeah, that sounds accurate.
Well, everyone's here, so I'm going to start. Here's the exciting attendance sheet. I know it's a minute early, but you know I'm going to go a minute over. So.
Yeah, I should be. Same here.
I will pray. Dear Father, we thank you for this day. Again, I thank you for this class. Just ask you to bless our work today, Lord. In your name I pray, Lord Jesus. Amen. Again, my apologies for minute 30 to minute 40 last time. Let me try to fix that. So there's just, so let me just recount. We have shown already that if beta and gamma are linearly independent and span beta is equal to the span of gamma, right, then the number of things in beta has to be equal to the number of things in gamma. Now, the context I'm saying here is for beta, gamma subsets of a vector space over a field, and the number of beta, number of gamma, less than infinity. All right, that's the context. So if we have two finite sets of linearly independent vectors whose spans are equal, then it follows that the number of vectors in those spanning sets must be equal. This is a straightforward consequence of looking at the vector space V being the span of beta. So that trace thing we did, we showed the traces were equal, going from the beta to the gamma to the gamma to the beta. That showed us the dimension of V was n for both, which is to say that the number of things in beta is the number of things in gamma. This we have already proved. So we have this. So then my next theorem, which I was spinning my wheels on a little bit, is this. If the dimension of V is equal to n, and S is a subset of V with the number of things in S greater than n, then S is linearly dependent, right? Now, first of all, in Math 221, this was just obvious, right? Like, in the context of column vectors, you figured this out fairly early on. If you have three two-dimensional vectors, there has to be a linear dependence, right? You can't have more than n linearly independent vectors in an n-dimensional column space, right? But I want to give you an argument which is good for an arbitrary vector space here. So here's the proof. Suppose, S is a subset of V, and the number of things in S is greater than n, where the dimension of V is equal to n. And then let's suppose S is linearly independent towards a contradiction, right? All right, so if the span of S is equal to V, right, then S is basis. And then S is a basis for V, right? Which implies what? The number of things in S is what? Is n, because we proved that for a finite dimensional vector space, any basis has n things in it. If one basis has n, any other basis has n. So the number of things in S is n. But of course, that contradicts plainly. Contradicting what? That we just said that the number of things is what? Greater than n, right? What's the other possibility? So, all right, either the span of S is V, or otherwise what? the span of S is not equal to V, right? Which means that, you know, which means that there exists X in V such that X is not an element of the span of S, right? But that's, I'm drifting a bit. Let me give, I mean, that's fine, but the real issue here is then, so extend S by adjoining such vectors to obtain, let's say, S prime, a basis for V, right? So like X is an element of S prime, let's say, but X is not an element of S. Do you understand? We're extending S to a basis for V. Now, why do I know I can do that? I know that from the extension theorem we had the other day. We can extend any linearly independent subset of a vector space to a basis for the vector space, right? That was the big theorem, actually. And well, what's the problem then? Well, the number of things in S is strictly less than the number of things in S prime, right? But the number of things in S prime is what? It's a basis, so by our dimension theorem, this is equal to n. But that means that we have, you know, n less than the number of things in S, which is less than the number of things in S prime, which is equal to n. But that is a contradiction. You can't have n greater than, you can't have n less than n. This is impossible. So again, contradiction. Therefore, we find S is not linearly independent, therefore it's linearly dependent. Right? That's the argument. Any questions? All right, so the other proof I have deprived you guys of is theorem 2.7.5. Like, it would be good for us to to think through this proof, yeah? But really the time to do that was last class, and we're past it, so I'll probably post a video about this where I'll like kind of walk through the proof of that. So you can expect a kind of standalone video on the proof of that, which is given on page 80 to 81. I think the proof is good, but it's a little bit involved, and it would eat up most of class, and I think we would be wiser to go on and cover the next material. So I'm going to then turn the page here and talk about linear transformations. So I mean, here's the deal, guys. Like, I need like about an hour of prep time for that one. Like, I need to like sit and think about it, make sure I've got everything in order. Because if I just try to go do it right now, bad things will happen. In contrast, the linear transformation material, I can just write theorems down and we can prove them together. You'll see it's rather easy. So, first of all, what's the definition of a linear transformation? What is that? So we start there, definition. Let V and W be vector spaces over a field F, right? Then if a function t from v to w satisfies the additive and the homogeneous condition, we say it's a linear transformation. T is a function from v to w, okay? Such that number one, it's additive, so like t of x plus y is t of x plus t of y for all x and y in v. And number two, t of cx is ct of x for all x in v and c in the field. Then we say t is a linear transformation. Right? We also would call it a linear map, all right? Because sometimes saying transformation is a drag, so map is easier to say. So it's a linear transformation or a linear map. Moreover, T is an element of the linear transformations from V to W. Right? So that's my notation for the set of all possible linear transformations from V to W. Okay? In contrast, if I just wrote like f was an element of the functions from V to W, just means f is got V for its domain and W for its codomain function. But a linear transformation is not just a function, it's a special kind of function. All right? So like some examples. We could have V equal to like smooth functions over the reals, and that's W as well, right? And so you could have T of F equal to like, you know, F prime prime plus F. This is a linear transformation because if you take the derivative, right, the derivative is, I mean, if you work it out, T of F plus G. We can do both conditions at once, right, guys? We can do like CF plus G, so like that. So we have like CF plus G prime prime plus CF plus G over here by the definition of T, which if we repackage that, we've got CF prime prime plus F plus G prime prime plus G using properties of the derivative, or second derivative in this case. And lo and behold, that gives us, you know, C T of F plus T of G. Now here I'm writing square brackets for the inputs because I'm thinking of T as an operator. You know, an operator has functions as inputs. That's more of an implied notation. It's not written in stone for us that we have to use brackets in that case. Like that's just me. That's the differential equations influencing me right now is what that is. All right. Another example, you could look like, you know, again, V is, we'll stick with the smooth functions as inputs, and we could do like T of F is the integral from 0 to 1 f of x dx. This is a linear transformation by properties of the definite integral. All right? That's a linear transformation. Example 3, we could do something like T of A is equal to A plus A transpose over 2. All right? And here T could be a mapping from, say, n by n real matrices to n by n real matrices. This would be an example of a linear transformation because the transpose has nice properties. What did you guys learn about linear transformations in 221? Do you remember? What was the big theorem? If T is a mapping from, Rn to Rm, then T of x is equal to the standard matrix of T times x, right? That was like, sometimes people call that the fundamental theorem of linear algebra. There's not good agreement on what the, whoa, that was not good. There's not good agreement on what the fundamental theorem of linear algebra is, but this is one candidate for that every linear transformation of column vectors then you can write T of x as its standard matrix times x, right? Just a reminder, this is, we can generate linear transformations of column vectors by matrix multiplication, right? Actually, it's an if and only if. If you have a function going from column vectors to column vectors, it's a linear transformation if and only if its formula can be written as a matrix multiplication. That is true. So the real reason I'm writing this, as I guess my example 4, is just to beg a question, which is, what's the matrix for example 1, 2, and 3? See, that question doesn't make sense because the vector spaces in question aren't column vectors. So we're not in Kansas anymore, right? You can't write down the matrix for those linear transformations. There's something else. Okay? Another example. So we do lose. Part of that's because these are infinite dimensional domains, right? So I can't even write down a finite basis. Like, we will learn how to find the matrix of an abstract linear transformation if the domain is a finite dimensional vector space in time, but we're not there yet. Yeah.
For example, 3, isn't Rn by n finite dimensional, just unspecified finite?
Oh, sure, but I can't write this formula as matrix times column vector. Not the case. However, you're right. Once I introduce a basis for Rn by n, with respect to that basis construction, I can write down a matrix multiplication which encodes this linear transformation, but in that context we will have to filter that concept through the coordinate maps. Okay. It won't be direct matrix multiplication. Like here I'm just saying straight up, if your linear transformation from column vectors to column vectors, that kind of function is a linear map, linear transformation, if and only if the formula is straight up matrix multiplication. It's impossible to have a linear transformation that's not that. In that context. All right, but anyway, example 5, if we have, f, a mapping from R to R, f of x equals to x squared. This is a nice function. We like this one. Is this linear? Well, we take, f of x plus y. What do we get? As you can see, we get 2xy plus f of x plus f of y squared, right? So f of x plus f of, so this trouble, right? It's not additive, right? It's not even homogeneous either, right? What happens f of cx? What happens there? Okay, all right, so fine. I've been calling item 2 homogeneous for like a long time. My brother does not like this. He says this is bad because in mathematics, this is sometimes meaning f is homogeneous degree 2. So in that sense, maybe it's bad to say that number 2 is homogeneous, but I don't know. I like to say it. We could say this. Number 2 means that scalar multiplication factors out of the linear transformation. We can say that. No one would disagree with that. And a lot of books would call that homogeneity of the linear transformation. But that is at odds with this like more general abstract terminology of homogeneous degree. Because we didn't pull c out, we pulled out c squared. That makes it, if you pulled out c cubed, it'd be homogeneous degree 3, et cetera, et cetera. Okay, so enough examples. A little bit more notation, lest I forget. The linear transformations from VW are also sometimes called HOM F VW. That's for homomorphisms from V to W with respect to the field F. I don't use that notation in here too much, but other people might. The thing that I will use in here more is that if V is equal to W, then we can talk about L of VV, right? And instead of writing L of VV, we'll just say L of V. And these would be linear transformations, or if you like, linear maps on V, right? Just linear maps on V. Just like we talk about a function on the reals, meaning its domain and its codomain are both what? Both real. The real numbers. So this thing keeps pulling. All right. So what on earth, what can we say about linear transformations, right? Again, so, there are so many things to say about linear transformations. I won't be able to say them all today, but I'm going to take a stab at saying as many as I can. So one thing I should say is, you might ask, well, what is linear algebra? Some people would say linear algebra is the study of vector spaces. Other people might say, well, linear algebra is the study of linear transformations. So I think they're both right, because linear transformations basically are tools to get from one vector space to another in such a way that we're, in some sense, maintaining some kind of addition idea from one to the other, right? So if we want to study the structure of vector spaces, that is in some sense tied to studying the structure of linear transformations. And a good part of this course is really devoted to studying the structure of linear transformations. Answering questions like, when are two linear transformations really the same transformation? When are two vector spaces the same vector space? What do we mean by same? Those are questions that we want to answer as we go on. To do that, though, we need to build some tools. So let's get at that. My camera keeps wanting to, it's fighting me. I put it someplace and then it drifts back the other direction. All right, so we'll start out real easy. Proposition for L, a linear transformation from V to W. Number one, L of 0 is 0. Number 2, L of the sum, I equals 1 to, let's say, n, of Ci Vi is equal to the sum, I equals 1 to n of Ci times L of Vi. For all V1 through Vn in V, and C1 through Cn in F. So what this first proposition here is saying two things, one of which both of which you probably already know. The first of which is, of course, 0 maps to 0, right? So the proof of that, we can dispense with that one pretty easily, right? So do you guys have an idea how we prove one? Yeah.
Can we just do 0?
Yeah, what makes 0? 0 plus 0 equals to 0. Very good. Thus what? L of 0 plus 0 is equal to L of 0. And then by additivity, which was one, my axiom 1, that's additivity, all right? L of 0 plus L of 0 is what? L of 0, which implies that L of 0 is equal to 0. There we go. Incidentally, that's a pretty good way to disprove something is linear, if that works for you, right? Like if you could say feeding 0 doesn't give you 0, well, it's not linear, done, you know, if there's a question.
So could we also use the second part of the definition and turn L of 0 into L of 0 times 0, and then pull one of the zeros out and say whatever L of 0 is, it's 0 times the result?
So you're like 0 is C times 0?
0 times 0.
0 times 0?
Yes.
Okay, I'm going to put a vector on this just so I can see what you're saying, but I see what you're saying. And so you're like L of 0 is L of 0 times 0. There's a vector on my L now somehow. Sorry. And then by property 2, we have, and this is just scalar multiplication, right, which I sometimes don't write in here. But any 0 times any vector is 0. So yeah, very good. There's an alternative proof. So we can either prove it by 1 or 2. Yeah. Which actually also shows you that if you have a mapping of homogeneous degree, whatever, it also must map 0 to 0 by your argument, because we could pull out 0 to a power, which is still 0. Interesting. I did not know, well, I guess I knew that if I thought for a second, but anyway, I didn't know. Number 2 is a statement about the natural numbers. So to do this properly, we should use induction, right? So for number 2, notice that L of C1 V1 is just equal to C1 L of V1, hence true for n equals to 1. Suppose that L of the sum I equals 1 to n of Ci Vi is equal to the sum I equals 1 to n of Ci L of Vi for some n in the natural numbers and all, possible C sub I and V sub I, all right? You'll forgive me if I define. Sorry, the legalism of math, it weighs on me sometimes. Anyway, there we go. Great. That's our induction hypothesis. Now we want to show it for n plus 1. What do? We look at L. So let C1 through Cn plus 1 be in the field, and V1 through Vn plus 1 be in the vector space. And we have L of the sum I equals 1 to n plus 1 of C sub I V sub I, right? Now by definition of finite sum, this is the sum of Cn plus 1, Vn plus 1, plus the sum I equals 1 to n of Ci Vi. All right, that right there is definition of summation. Right? Remember, the definition of the finite sum is made recursively in this way. That's how we actually define finite sum. Now, so then what's the next move? The next move is to pull the Cn plus 1 out, L of Vn plus 1, right? Plus L of this. So all I've done at the moment is I've used the axioms for the linear transformation to first of all split it up into the sum and then pull the constant out. If that's okay, I'm going to write that just one step rather than two. Right, so that's by 1 and 2 for the definition of linear transformation. And then I can use the induction hypothesis, right? So by induction hypothesis. And then finally, this is nothing more than the sum I equals 1 to n plus 1 of C sub I L of V sub I, definition of finite sum again. And hence, by induction on n, 2 holds. Can you guys put into words 2? Like if you wanted to remember 2 as a slogan about linear maps, how would you say it? What are we saying? We're saying L of a linear combination, right, is a what? A linear map takes a linear combination of vectors to the same linear combination of the images of said vectors. See, the images of V1, the image of V1 is L of V1. The image of V2 is L of V2, and so forth. So what that says is that the image of a linear combination of vectors is the linear combination of the images of those vectors. So with that in mind, the next result will be very unsurprising, which is if we have proposition L, an element of the linear transformations from V to W, if S, a subset of V, is linearly dependent, then L of S is linearly dependent. So I think without loss of generality, if S is linearly dependent, that means we have a a non-trivial dependence in S, right? So, so the proof goes like this. S linearly dependent means that there exists V in S, right? And V1 through Vn in S, such that V is equal to a sum I equals 1 to n of Ci Vi, right? I'm taking the liberty of stripping the index off the dependent one. When we did this before, we solved for the jth one or something, right? But we don't have to be stuck on that notation forever. Just the one we're finding the dependence of, let's unadorn it. Just call it V, all right, great. So we can build one as a linear combination of the others, then, well, check it out. L of V is equal to a sum I equals 1 to n of Ci L of Vi, right? But hence L of S is linearly dependent. What does L of S mean, guys? Don't let that wash over you. L of S means L of X, such that X is an element of S. It's the set of all possible outputs under L with inputs from S. It's also called the image of S under L, all right? It could be an infinite set, it could be a finite set, right? Depends on whether S is infinite or finite, whatever. But there you go. Yeah. Now, definition. Given T, a linear transformation, so I'm back to T again. If you look at these notes, I can't make up my mind whether I want to tell a story about T or L, but I'm back to T again here. So the kernel of T, all right, is X and V such that T of X is equal to 0. And the range of T is equal to T of X such that, well, T of X, find T of X such that X is an element of V. In other words, that's TV, right? It's the image of the whole domain under the transformation, the range, right? If we said T was surjective, what could you say? Reminder, right? T being surjective here would mean that the range is the whole, yeah.
Does that mean the function is 1 to 1 or?
No, surjective meant, surjective was onto.
Oh, I just got confused.
It's okay. So there's still time. So if T is onto, what is T of V equal to? If T is surjective, what is T of V equal to here? Remember, T here is a mapping from V to W. That's what that notation means, the linear map from V to W. So to say T is surjective is to put an equality of this in W, right? This is what we mean by surjective, right? Surjectivity of T. So that's kind of next on our list is like, okay, so what can we say about injectivity and surjectivity of a linear transformation? All right, and so here's the theorem. If we have T, a linear transformation from V to W, then T is injective if and only if the kernel of T is the set just containing 0. First of all, this is very special to linear algebra. If you think back to my example 5, right? Is that function 1 to 1? Is it injective? Well, no, right? F of minus 1 and f of 1 are both 1, because minus 1 squared and 1 squared are both 1, right? So those different inputs give you the same output. The analog of the kernel for my example 5 is still just 0. The only thing that maps to 0 is 0 for x squared, right? The graph y equals x squared just bounces off the origin, right? So what I would call the kernel of f is 0, and yet it's not 1 to 1. So you see this theorem is special to linear maps. It's not true for like nonlinear maps generally. Example 5 already shows you that. So, okay, let's prove it then. Go ahead, no? So which way do you guys want? It's a biconditional proof, so we got to go, you know, got choices here. I want to go the forward direction first, or? Okay, forward, all right. So what do we get to assume this way? Assume T is injective. All right. Suppose x is an element of the kernel of T. Then T of x is equal to 0 by definition of kernel. Right? But what else do we know? You guys gave me 2 different ways to prove it today. T is a linear map, right? T of 0 is equal to 0 by previous proposition, right? Hence, T of x is equal to 0 is equal to T of 0, right? But we said T is 1 to 1. What does that mean then? T is injective. Injectivity means T of x equal to T of 0 means x equals to 0. Right? So, apparently, the set containing 0 is a subset. So kernel of T, I picked x in kernel T, right? And I just showed x is equal to 0. So I believe that shows that the kernel of T is a subset of the set containing 0, right? But it's obviously also true what? T of 0 is equal to 0, therefore 0 is an element of kernel T. And so the set just containing 0 is also a subset of kernel T. So we have what? Double containment, right? So hence, therefore, kernel T equals to what? The set containing 0, right? So that completes the forward direction of that proof. This last sentence I wrote, like, I don't usually take up points if you don't do quite all of this. Like, I think once you get this step, it's actually pretty much clear that the kernel is equal to the set containing 0, because the calculations I've already shown here already indicate that 0 is an element of the kernel T. You know? So you would be well justified after what I, to not write what I wrote in blue and then just put equals the set containing 0 right here. I wouldn't take points off. Like, I think it's actually clear. But just to be clear. To be less clear by being more clear, there's the blue. Sometimes. Allegedly, the more rigorous proof is the more clear one, right? But sometimes it's actually not true, Less is more. Okay, so reverse direction. We assume what? The kernel of T is equal to the set containing 0. All right, let x and y be in the vector space, and suppose T of x is equal to T of y. What is our job here? To show T is injective, what do I have to demonstrate? X is equal to y. If we can show x equals to y, we have shown T is injective, right? Observe T of x minus T of y is equal to 0, which implies that T of x minus y is equal to 0, which implies that x minus y is in the kernel of T, which, by the way, is the set containing 0, which implies that x minus y is equal to 0, which implies that x is equal to y, which implies that T is injective. And we're done. Yeah? So, there's that. Now, next question up is, what does a linear map do to subspaces? All right? What does a linear map do to subspaces is the question. And the answer is, it plays nice. It plays very nice with subspaces. So, like, here's the theorem. If T is a linear map from V to W, right? Number one, if V sub naught is a subspace of V, then the image under T of V naught is a subspace of W. And also, number two, if W naught is a subspace of W, then the inverse image, T inverse of W naught, is a subspace of V. All right? So the proof of both of these rests on properties of a linear map as well as the subspace test. All right? So let's work them out. Notice that inverse does not mean that the mapping's invertible. That is the set inverse, right? So I'll work on the proof of 2, since that's probably the more confusing one. Let's just set things in motion here. T inverse of W naught, by definition, means x in V such that T of x is an element of W naught. It's the set of all elements in the domain which map to W naught. All right? So note 0 is an element of T inverse of W naught, since T of 0 is equal to 0, and 0, of course, is an element of W naught, which is a subspace of W, right? So thus, T inverse of W naught is not empty. It's got 0 in it. 0 mapping to 0 means that 0 is in the inverse image. All right. Let x and y. Actually, let me use A and B here for a second. Let A and B be elements of the inverse image of W naught. And we'll let C be an element of the field, right? Then there exists x and y where? In W naught, right? Such that you're like, I don't know what the next part of your sentence is. You're not done saying the sentence, so it's not mine. Come on, leave me alone. But such that what? Well, such that T of x is equal to A, and I'm sorry, I'm getting things twisted here. Give me a second. I could just make it through one day without doing something stupid. Let's try this again. All right. So I need to pick x, I'm going to say x and y in T inverse of W naught. All right. That's a bad choice of letters because I have the x up here. Fine. It is what I wrote it, so let's deal with it. Then T of x and T of y are where? By definition, those have to be elements of? No. X in here means T of x is in W naught. So these are both in W naught. Which means that T of x plus y, which is T of x plus T of y, right, is an element of W naught, which is, by the way, a subspace of W. And also, T of Cx is C times T of x is also an element of W naught, which is, because it's a subspace of W. Do you see what I'm saying? We know T of x and T of y are in the subspace W naught. So the sum of those must again be in W naught, by the subspace being a vector space. Scalar multiple of something in W naught must again be in W naught. So I have now shown that t of x plus y and t of cx, let me just repeat this again here. So we've shown, thus, t of x plus y and t of cx are elements of w naught. But this means x plus y and cx are elements of t inverse of w naught. Because these are elements, these are vectors in V which map to w naught, which means they're in the inverse image of w naught. Hence, t inverse of w naught is a subspace of V by subspace test. Yay! So that's the proof of 2. Proof of 1 is a little bit easier because it doesn't involve inverse image. And you guys are not used to inverse image. I'm generalizing on the assumption that you're like all other math students I've ever taught. Sans like 5 freaks of nature who just have this like, hard-coded into their brain somehow. I was not such a person. It took me a while to get used to this idea, all right? The inverse image of a set. But you can do it. It's not that bad. You just need to sort through what it means. The inverse image of W naught is the set of points in the domain that map to that. Now the other one, the proof of 1, notice that 0 is an element of V naught, which implies that t of 0 equals to 0. And t of 0 equals 0 implies that 0 is an element of t of v naught, right? Because it's since 0 maps to 0, that means that 0 is in the image. And then if we have x and y and t of v naught and c in a scalar, then there exists a and b in v naught such that a is equal to t of x, b is equal to t of y. So thus, a plus b and ca are also elements of v naught with t of ca plus b, c t of a plus t of b, which by the way is c x plus y, and that's an element of t of v naught, since ca plus b is an element of v naught. So there you go. That's the proof of 1. The proof of 1, again, 0 maps to 0, so 0 is in the image. And if I take two things in the image, right, that means there have to be things that map to it, namely a and b. But since those things are assumed to be in the subspace, there's some and scalar multiples in the subspace. And then if I look at t of ca plus b, well, I get c t of a plus t of b, which is exactly cx plus y. Oh, look, cx plus y is in the subspace. Therefore, by the subspace test theorem, I'm missing my conclusion here. Therefore, t of v naught is a subspace of W. Okay, so conclusion for class today. You tell me, kernel and range, are those subspaces? What do you think? They are, right? Because the kernel is the inverse image of what? The subspace. It's the inverse image of the zero space, right? That's what that is. So it's a subspace by my theorem over there. And the range is the image of V. Is V a subspace of V? It is. So that's also, so yes, range and kernel are subspaces. Anyway, that's it for today, guys.